Welcome to the PASCO webinar on OpenSciEd, exploring PASCO OpenSciEd physics. Where does electrical energy come from? Thank you for joining us. What happened in Texas? In February 2021, over 11.8 million Texans lost access to electricity to heat and light their homes, store their food, and charge their devices. For many people, the power outages lasted for several days. Hundreds of people died as a result. So we're going to watch some quick clips about what happened in Texas. If you were with your class, you'd be doing this with your class. Since you're here with me, do keep track of maybe anything notable you hear in the news clippings for sharing later.
Night. Some 4 million without power, and this image right here sparking anger in Texas tonight. Houston skyscrapers brilliantly lit, while neighborhoods surrounding downtown are in the dark. Families without heat, without power. At least 140 cases of carbon monoxide poisoning in Houston alone. That woman and an 8-year-old girl dying after authorities say they were trying to stay warm using the car in the garage.
Right. So we'll watch another one.
Another round of winter weather. In Texas, nearly 3 million households are still without power following Monday's snow there. The power grid in Texas is not connected to the federal grid. Snow and cold put stress on that state's electrical grid, leading to rolling blackouts.
And our last video is, in fact, an international. This blackout in Texas made international news, not just national.
Record-breaking cold temperatures.
All 254 Texan counties have imposed a winter storm warning. That's never happened before. President Biden has declared a federal emergency, freeing the way for disaster relief.
The severity of the cold weather that is about to be experienced here in the coming days is unprecedented.
There are power cuts as the state tries to cope with a huge spike in demand for electricity. Despite its fame for oil, Texas leans heavily on wind power, but now many turbines are frozen solid. Millions have been without power.
All right, so we got to hear from those news clips, and maybe you heard something interesting, so keep that in mind for a little bit later. Because first I want to look at this graphic that we have that has power outages by day in Texas, Sunday through Thursday during this time period, and start thinking about what do you notice or wonder about power outages and these trends that we might see come up. So we can see on Sunday at 7 p.m. we had 100,000 customers without power, about 1%. Monday, that jumps up to over 1 million customers. By Monday night, 10 p.m., we're already at 4.5 million customers without power. Tuesday, it stays at about that at 4.4 million customers. Wednesday, it gets a little better at 3.4 million customers. And by Thursday, it's dropped down to about 500,000 customers without power. So this was the power outages that we saw throughout Texas during this storm period. And so now both the anything you found in the news clips as well as from the graphic and maybe some trends, and I'll pull up that image back here in a second, is let's start thinking about sharing what we noticed or what we might wonder. So you have this QR code you can use for your phone with your phone's camera to go to our Padlet. The Padlet looks something like this. So you can add a noticing or wondering or both. And if you're like, but I understand what this is, because many of you are probably classroom teachers, what might your students notice or wonder about these incidents, either from the news clips or from the graphic? There's also a URL that you can go to if that's more comfortable that Glenn has posted in the chat. Thank you, Glenn. So I'm just going to give us about 2 minutes of thinking time. So nothing fancy, just quick. What do you notice or wonder about what happened in Texas? Or what might your students notice or wonder about what happened in Texas? I see we got a couple people writing. Excellent. Someone stated that they didn't know it snowed in Texas. Yes, it does in fact snow in Texas. Not normally as much as it did though. So we got a studious newt, a whimsical oyster, a passionate spider. Let's go. Oh, we still have people writing, so I'll let them finish. Mhm. Right. And we have one more person writing, and I, of course, will let them finish, but I'm going to bring this over so we can look at it. So we got a couple noticings. I didn't know it snowed in Texas. It does, just not normally this much or this severely. Outages got worse over time, then got better. Snowstorms are more common due to climate change. Um, yeah, and then there are windmills in Texas. All right, some things we might wonder about. Why didn't everyone lose power at once? Why downtown had power, but the surrounding area had no power? How cold was it when the system failed? Why did the outages start at the coast? And why were the areas in the middle of the state lose power for the longest amount of time? Oh, and how maybe the cascade of outages spread. Excellent. So with your students, you probably spend more time going over these, talking with them, but obviously we're a quick webinar. So we have those. And then once you have your students have these noticings and wonderings, you also want to expand to broadening it to related phenomenon such that might affect them personally. For example, in California, fires are one of the major blackout causes. Also, blackouts done purposely to prevent fires. There could be hail or snow breaking wires, different animals chewing through these wires, wind blowing down infrastructure, fallen trees, and even possibly just running out of fuel or issues at a power plant. So that way you connect it back to what might be going on in your students' lives or things they've heard of. From here, we look to build an initial model. So why might some buildings in a community experience a blackout while others don't? So we want our model to include how energy might transfer between buildings, why one building might get enough energy while the other does not, and where does the energy come from to power the electrical devices in each of those buildings. So I'd like for you guys to draw or jot down any ideas you have for how your model should look. This could just be a quick sketch, maybe write down thoughts you might have, and we will look to compare that in a second. So let's say, again, just 2 minutes, just some quick ideas you might have about how energy might transfer between buildings, why one building might get enough energy while the other does not, and where does the energy come from to power the electrical devices in each of those buildings? Say, a minute 10 extra thinking time or writing time. Yes, so this is just on your own paper right now, or whatever you have at home, or, maybe you have a wonderful imagination and you're drawing it inside your head. And we'll talk about them in a second. Well, more like 30 seconds. All right. If you were in a classroom, you'd have your students do a quick gallery walk after writing their initial model so that they can see and expand their thinking. But since we are in a webinar, instead we're going to use this example of a student model, classmate A's initial model. And so compare your diagram or ideas to to classmate A's initial model. So we have our noticing wondering here, but now let's think which part of A's initial model are the same as your model or what you think your model should be, and which part of A's initial model are different from your model or what it should be. So again, in that Padlet that you might still have up, looking at this diagram, what is the same as a model you would draw or have drawn, or what might be different from this model? Again, just a quick 2 minutes of your ideas. Oh, already have studious newt and passionate spider on it. Oh, and we have 5 more writing. Excellent. All right, say 1 more minute of writing time. So if you could finish your thoughts. Thank you again so much for participating. We have our last classmate finishing their thoughts, but let's quickly do go through what we have. So which part of A's initial model are the same? They start with a power plant, right? There's some sort of source, power lines, but some of these power lines are up, some are down due to storms or other issues. There's some distribution from this to homes. We could add that industry versus home sites, that there's some example of power loss. Great. What might be different? They did a better job with labels than me. It's true. Labels are always wonderful to have. Oh, some houses have their own generator. That's true. A lot of people might be aware of power outages and have generators themselves. Um, Downtown buildings are equipped with generators. Oh, solar panels. Yes, absolutely. Um, Different could be a different way that the power failed. Oh, we included wind turbines. Oh, solar and wind backups. You guys are very prepared in your model. You're ready for these power outages. Excellent. All right. So once these initial models have been made and you have talked about them with your class, you want to develop some sort of record that we agree on. You can also have competing ideas, normally often signified by question marks, and then also talk about the initial energy transfer for these models. So here's a sample consensus model. We see that it agrees with a lot of what you said. There's some sort of power plant, maybe there's wind, generator, coal. People also mentioned solar. There's some sort of power lines. I guess this class also mentioned the idea of undergrounding wires. There's a big push to do that in California due to the fire danger. Some sort of breakage occurs that shuts one community off while the other community stays on. And then from here, you can also start adding, well, what's the general name for this system, and start modeling where the energy transfers and any possible other interactions. So with power plants, maybe some students have seen that, well, maybe there's some sort of turning or burning involved in these power plants. Our power plant is the initial source of energy, and this source then sends electricity through the transport lines, and these are then transported to communities that the electricity somehow heats or lights homes. So this would be your sample consensus model for your class. And then once you have that sample consensus model, you want to start thinking, well, how do we answer some of those questions that we have? How do we confirm what we know? So can you use the class's initial consensus energy transfer model to explain the pattern of power outages we noticed in Texas in February of 2021? What additional data or information would you need to explain these patterns? And so students begin to plan how might they test your ideas. And obviously, as the teacher, knowing the tools that you have in your classroom, start to guide these ideas. There's also, if you're familiar at all with OpenSciEd, you have probably heard the idea of the driving question board. This is a major part of every OpenSciEd unit. It's where you keep track of all of your students' questions and ideas and start to group them into major things and into major questions that we want to solve and answer. So that leads us to talking about just the general OpenSciEd instructional model. The goal here is to always be figuring out instead of learning about. So just like in OpenSciEd, we started with our anchoring phenomenon. We all shared this experience together. Then we start soliciting questions and drawing models and starting to think, well, what do we know and what don't we know about our anchoring phenomenon? And then from there, navigate to, well, now that we have these questions and this information, what additional information do we need? And then that leads to my personal favorite of every one of these is the investigation routine, which is what we're going to focus on today and how we incorporate PASCO technologies into this. And so this is where we can develop evidence to support and explain different parts of the phenomenon. Of course, the model continues after the investigation with some additional problematizing, putting it together, navigating additional investigations until we have all of our questions answered. Now, so we can kind of see what the OpenSciEd model is. So what does that mean for the OpenSciEd certified PASCO version? So what hasn't changed and what has? Well, what hasn't changed is it's still designed for NGSS and three-dimensional learning. It's a storyline-based instruction. Units are anchored by that core phenomenon, and lesson sequences are coherent from the student perspective and driven by their questions. Well, then what has changed? Well, PASCO technologies have been infused into investigations and demonstrations as appropriate. Physical equipment is provided in the PASCO equipment kits, and curriculum resources are organized and delivered in the PASCO portal. Now, and you can find more at pasco.com/OpenSciEd. Now you might wonder, well, PASCO Portal, what is that? The PASCO Portal is a solution that we designed to integrate with single sign-on support as well as learning management system support to work with local ITs at each district. It has a core curriculum, not just OpenSciEd, but also our essential physics and essential chemistry. There is a experiment library that has so many experiments, both by different subjects and different levels. There are the PASCO Academy, which has multimedia resources. There's professional learning opportunities. There's technical support, and of course, PASCO's software. So there's a lot here involved in the PASCO portal. So much so that we're excited to say that we are the Educators Pick Best of STEM in 2025 for Best Digital Ecosystem for STEM Teachers. And we can learn more at pasco.com/portal. So the resources on Portal. So there are resources provided for Unit P1. What resources are there and where do I find them? So I'm going to pull up Portal here. See, make sure I didn't log out. Cool. So this is my portal. I do have some pinned resources, but I'll go through the standard menu to access them. So we're going to go to OpenSciEd, go to High School Physics, and we're here in the first unit, P1. So you can see that we start by having unit level teacher files. So these are general things that you might want throughout the unit, including the unit overview, which as it sounds is a unit overview for the entire unit. Let's take a quick look here at lesson 1. So we actually did a very, very truncated version of lesson 1. You can see we have all these student files. You might already notice that there's a lot of reading articles that I'd never mentioned. So instead of asking you guys to read 6 articles, I picked a couple news clips that we could watch together instead. Also notice that there are multiple formats for each of these. So editable, such as the Google documents, as well as Microsoft Word, and uneditable PDF files. So however you might want to distribute that. There's also both English and Spanish versions of all of these student documents. Outside of the student documents, we have, of course, our teacher files. So our lesson plans, the slides, and if there's any additional teacher references that you as the teacher might need to know. Let's go ahead and look at the teacher edition, which is the lesson plan for this lesson. We start each lesson with the guiding question for that lesson. What can we learn from a blackout in Texas about producing reliable energy for our communities? There is a lesson summary, as well as a next lesson and previous lesson summary, if there was a previous lesson. It lets you know which different NGSS standards that we are building towards, as well as what students will do to build towards those standards, and then a more generalized what we expect students to figure out through the course of this lesson. Next, the learning plan snapshot is a great way to get a quick idea of the different parts of the lesson. It includes how much OpenSciEd expects one to take, as well as a summary of what will happen during that segment. It also has the materials listed out quickly so you know what will you need to prepare for that particular segment of the lesson. But if we want to get more in depth with the materials section, there is a full materials list that notes everything that you might need, how much per student, how much per group, how much per class, and where is it located, and if there is a PASCO part number associated with it. You'll note none of these have them because the most are found in the portal, so they are digital resources. Of the ones that are not found in the portal, these come in the consumable kit, so they're not particular PASCO items. We'll talk about kits in a second. And it also lists if things were created during the lesson, so you know that this isn't some item you need to find. It will be created throughout the teaching of the lesson, as well as any materials prep you might want to do before the lesson begins. And then goes really shortly into where we are hoping to go with this and where we're not going, and then into the lesson itself. So that is the teacher edition of the lesson plan, how you can find it. Now, what are the PASCO equipment kits? So where to find PASCO provided materials? I already mentioned this one. This is the Unit P1 Classroom Consumable Kit. So these are just your general classroom items, colored pencils, sticky notes, chart paper, Ziploc bags, Sharpies, that sort of thing. And just this is a quick picture of some of the items included. The next is the classroom non-consumable kit. So these are often for classroom demonstrations or large classroom activities. You can see pictured here. These are some of the things that will be used in both Lesson 2 and Lesson 5 of Unit P1. And these are items that you can use across years. And then last and certainly not least is the lab group kit. So these are the kits that you would have per group for different investigations. This is where the bulk of PASCO technologies are infused. You can again see some of the items that are included in the P1 lab group kit here. So getting back to our OpenSciEd lesson, each lesson is added into different segments. So we have that first lesson segment is how does electricity transfer through systems to power communities and what causes instability in these systems. So that goes from lesson 7 to lesson 8. Lesson 2 and 5 are our first big investigations, and those lead us to a transfer task. The transfer tasks are basically large assessments where we're hoping for students to take their knowledge that they've learned here and transfer it to a similar but novel case. And then the second segment is what design solutions could improve the electricity systems. We're going to be focusing on the first one because that's where our investigation is today. And note this unit is 11 lessons with 28 days of instruction expected. So we're back into lesson set 1. And so let's remember our sample consensus model. We figured out there was a source, a transport, we have different communities, and somehow we know electricity comes from our source and goes out. We also agreed that something about the power plant is creating energy, some sort of coal, wind, solar, or generator must be involved. And so in lesson 4, they just finished learning about the different types, such as we talked about wind, coal, solar, natural gas. And then in lesson 5, we actually look at, well, what's going on inside of these different power plants? We start out with a wind turbine power plant and have students, what do they notice? What do they wonder? And then we start to model and diagram the basics of each of these plants. So for the wind one, it starts with wind, blades are pushed, there's some amount of spinning that happens, and then there's a generator involved, and we get electricity. With the natural gas, there's some sort of gas, we burn it, it heats water and steam, which turns something, and then there's a generator involved and we get electricity. And so the natural question that comes out of this is, what is a generator? What is inside a generator? And so we pass out these small dissectable mini generators. They can spin them, turn on LED lights, and start to get an idea of what is the internal workings of a generator and what are the key components we expect them to find. So with the class, we make a list of the parts of the generator that you were able to observe or infer. So key parts that you want your students to get out of that is there's some sort of coil of wire. Maybe they even note that it's made of copper. There's a magnet or magnetic strip involved, some sort of crankshaft, axle rod, something that spins, insulated wires that lead out, and often a protective case to hold all of it together. Now, we want our students to begin investigating this and start figuring out, well, what does each of these parts do? What's the purpose of them? And it would be great, to have a way to swap these parts out and move them. So we developed the PASCO Modular Circuits Generator. Uh, you can see it pictured here, and I'll show it here in a second. We have our wire. This is our modular circuits kits. This is our copper coil. We have this housing for 8 different magnets, and we have this crankshaft that we can use to spin it. So we have here the PASCO Modular Circuits Generator. We can see I can quickly turn it to spin. Note this red color, we have painted all of the north red just so it's hopefully a little more visible for everyone at home or wherever you're viewing us today. They do come in just blue. The casing is very hard to mark up, actually. Glenn did an excellent job of getting the red to stick. But on that note, it will be very hard for students to damage the magnetic casings. So now that we have our modular circuits generator, please post in the Zoom chat. How will we know that our generator is successful, or how might you expect students to know that the generator is successful? And how would we know that it's working well? So just really quick in the chat, how can we know that the generator is successful, that it actually works as a generator? I've told you it's a generator. I've said I have all the components we need. How do we know that our generator is successful and it works as a generator? Yes, James. Yeah, let's just connect it to light bulbs. And we can really quickly snap in our 2 LED. I went with 2 because it fits, and that is what's included in the kit. So now we can start seeing, well, does this light up? And then next, how do we know it's working well? This one's maybe a little more nuanced, a little trickier. So if it's successful, we should be able to turn on lights. How can we compare it to other things to know what's working well and what's working not well? Yeah, we could start maybe looking at the brightness. Some other things students have mentioned is how well it's continuously lit, if it's maybe flickering a lot or only sometimes turns on, because I'm a human, I can only spin this at the speed my hand will go, so it's not as consistent. Or even some students have thought, how easy is it to light, right? Am I going to have to spin this really fast? Or can I spin it nice and slow? So now we get to the fun part, at least I think so. So with our class, and obviously they would be doing this in their lab groups, but what about the generator can we change to affect how well it works as a generator? And I'd really like to hear your ideas here, again, in the Padlet. That way we can not just test what I want to test, but test what you want to test. So again, in the Padlet, and I will let but this last question here, what design changes should we test? So what do you want me to try to change on here such that we can change the quality of the functioning of this generator? So what should we test? And there's also a heart button here. So if someone posts an idea and you're like, oh, that one, that's the one, feel free to put a heart to make sure I know which ones we definitely should do. Spin it fast versus spin it slow. Easy one, absolutely can do that. Change the path of the lines. If I'm interpreting that correctly, maybe we could change, I could take one of these lights off. Gear ratios in the generator. I don't have an easy way to change the gear ratios, unfortunately, but that is an excellent idea. But ultimately, I could just try to spin it faster or harder. But yes, if we change the gear ratios, that would make it easier or harder for me to spin. Speed of rotation, battery operated hand crank, yes. Magnet strength. So I can't change the magnet strength, but I absolutely can change the magnetic field strength by removing some of these magnets. Yeah, I can change the number of magnets. So all 8 of these magnets are completely removable. Well, no one's mentioned it. Well, let's do those. And if you have any more ideas, I will scroll through these, add a different combination of magnets, or add more devices, magnet orientation. Yep, we can flip those magnets around. All right, so let's do the base one, which is most people said we'll spin it. So with testing our generator, just to let you know, our starting coil is 1,000 turns and has 0.25 millimeters in diameter. Our starting orientation, in case it's hard to see at home, is a north-south alternating for all of them. So let's just do a very basic spin. So I have to spin kind of hard. It's not particularly difficult. You can see it flickers based on there. If I spin a little harder, we get a bit more consistent lighting. So we can see that spinning it slow obviously has an impact. Spinning it fast helps create a more consistent light. Let's see, we talked about magnet strength. So has anyone added more coils, environmental factors? Okay, so no one's told me exactly what orientation they want to do, so I have some ideas. So I'm going to do all north. So I'm going to flip all of these around so that north is all the way out. All right. Glenn, how visible is that from your screen? Oh, and then note, if you're having a hard time viewing, there should be a way to slide in between both the shared slideshow and the shared video so that you could make the video larger and hopefully easier to see. So now that we have all north facing out, you can see the red, we can see that the normal speed that got light doesn't. Maybe if I spin it really hard, there might be flashes of brightness, but it's not something I can keep up consistently and certainly not while talking. So we can see that that one didn't work. We can change the number of magnets pretty easily as well. So let's remove some of these. So now we have still all north facing out, but just 4 of them. And interestingly enough, and maybe it might be confusing for your students, is that actually was easier to light up than the all north. So north-south worked best, but north-north with less worked better than all 8 facing north, which is kind of a bit of a conundrum for students to puzzle out. We can also swap out our coils. So, right, we can add more coils. So we have an 1,000 turn here, but since this is already difficult, let's swap this out with a 2,000 turn coil. So we now have our 2,000 turn coil in place. And remember, it was difficult, but not impossible for me to get it to light up. And now it's pretty easy to get a consistent light going, even with 4 all north-facing magnets. So this kind of gives students an idea. Additionally, no one mentioned it, I think, unless I missed it. No one mentioned it, but we also, and I got to change formation for this to be visible, because these are 500 turn wires, but these are 2 500 turn wires, one with, I had this in my brain a second ago, one that is also 0.25 millimeters in diameter, and the other that is, I believe, 0.37 millimeters in diameter. So you can actually look at the different I dropped my clip. There it is. You can compare the difference between the different diameters, but to do this, I will need to go into the much more favorable north-south formation. And again, if anyone has any additional things they want me to test, feel free to still write it and I'll check before we move on.
On the Padlet, Amari mentioned environmental factors.
Environmental factors such as?
It's not specified, but I wonder something like temperature.
That is an excellent thing for you to bring up. All right. So we can see, you see that light up? Barely. And if we swap it out, if I remember correctly, both of these are hard because they're 500 turns, but this one is thicker wire, so it's a little bit easier for me to spin and get lights going. Great. Yeah, maybe there are some environmental factors. So we just sort of did a really quick version of the handout that is provided for this lesson. It goes into different design challenges. We talked same thing, class criteria for success. It gives options for them to try just to make sure they see some of the phenomenons we hope for them to see in this, and then goes through all the different ways they can change it. And of course, this is an editable document, so you can change it to match whatever your class is looking to change. This leads us into lesson 5 that I'm going to summarize really quickly, where they look at not just does it produce electricity, but actually the different magnetic fields that are produced, and learn about the relationship between magnetic and electric fields, and learn that it's not just the fact that these magnets are near that are causing magnetic field, it's that the coil itself, when there is electricity running through it, creates a magnetic field. Which leads us very quickly into this simulation where they can see the electrons moving through a wire, and we can start changing some of the things that are a bit more difficult to change in real life, such as the wire material, the wire temperature, the wire diameter. They can make it change more, the wire length to source, because there's only so long we want to make this in our classroom, as well as changing the circuit and adding things. So in OpenSciEd, there are both plenty of physical investigations as well as simulations. And from this one, they actually do and work to test the temperature using ice to cool it down and see if there is any change in the current. Once they learn about this, this leads them into their lesson 6 assessment, or the transfer task. So this is what the transfer task looks like. It is a motors transfer task. So once they've hopefully learned about how spinning a magnet around a coil creates an electric current and creates electrical energy, how can we use electrical energy to now spin a crank or shaft? So basically, they turn that around and apply what they currently know to a novel phenomenon? However, if you've taught this before, you know this particular idea can be very difficult for students to grasp. So there is actually a built-in secondary transfer task for if you need a reteaching moment, and they do this with transformers. So this is one of the major assessments in the first physics unit. Now, you might say, well, that's just one assessment. What do I do for the rest of these lessons? Well, there's an assessment guidance in the unit overview called the assessment system overview. And that goes over just where are some basic places where you should assess, some pre-assessments, as well as the different lesson level performance expectations and ways that you can do formative assessment, summative assessment, and what ideas you should be listening for each of these students and their learning. Now, that brings us to, we have on-demand professional learning in the PASCO Portal. This includes curriculum training with certificates, both for the middle school and the high school versions of the PASCO certified version of OpenSciEd curriculum, as well as video tutorials that go through how to access and navigate the portal, and as well as using SparkView. Many of our investigations use our SparkView software. However, this particular one does not. We have also partnered with Better Lessons to provide live virtual workshops, on-site workshops, asynchronous courses, and follow-up coaching. That way your district can choose what works best for your professional learning needs. If any of this interests you, and hopefully you can contact your regional representative at pasco.com/support. Also, just launched today, we have a free trial to PASCO Portal. You can either follow this at the QR code or the link www.pasco.com/portal-free-trial. And I see Glenn has already posted both links in the chat. And it seems we're running a bit early. So that's the official end of the webinar.